There we go. And the recording's on, so welcome to our official start of Big Data for today. And today we're going to start talking about this indexes concept that I've been promising we're going to talk about. And this is going to be the key thing that's going to make all of our big data operations that we're going to want to do, and the rest of the semester make them fast instead of just correct. And so I'm going to share my screen and we'll start talking about that. Okay, first though, I'll just show a few of these baby pictures. You might have seen them. I posted them on the GitHub issues. And one of the things that I want to highlight, just talk about these PS statements down here, first of all. So at the beginning of the semester, we mentioned that, or I was talking about, so one of the maybe motivations for studying the things in this class is the good salaries that you get if you end up working at one of these top tier tech companies, either in a CS or a data science role. And one of the things that, so I guess people talk about a lot about the good salaries at those positions, but one of the things they don't talk as much about is the sort of benefits associated with those positions. And one of those is good parental leave. So all of the major tech companies have different policies, but they're all pretty generous. And the one that is the best is Netflix, and they offer a full year of paid time off for both mothers and fathers. Some other ones are Amazon will provide the paid time off for your spouse, since most companies in the US don't provide any paid time off. It's not a federal law or even a state law in most states that you have any sort of parental leave, but these companies do it. And then the next PPS postscript is, so today is Cesar Chavez Day, and I wanted to do something a little bit special today for that. And so Cesar Chavez Day is celebrating Chavez's work for labor rights, specifically migrant farm workers in California. And so I wanted to also point out that the tech companies, despite these generous offers that they make, they have been found to be illegally colluding with each other and breaking labor laws in order to drive these salaries and benefits down. And so it's work like Chavez that gets us these good benefits. We'll also talk probably next week a little bit more related to Cesar Chavez, and in particular, how when we start talking about full text search, so that'll be based on some of these techniques using indexes that we'll talk about today. How do you efficiently search through full text? We'll get into some complicated scenarios when you have a name like Cesar Chavez or any text that contains, say, accent marks in it, and how those get represented inside of the Postgres database. So we'll revisit Cesar here in a little bit when we talk about full text search. Maybe one last thing is that I realize there are some GitHub issues and a whole lot of emails that I haven't had a chance to respond to yet. And so I'll do my best to get to those as soon as I can. But if anybody has questions about homework sort of issues, then I'll be available after class today or during office hours today to answer those. And so my hope is that you'll have enough time to get your questions asked and be able to complete the assignments. Okay, so for this week, I'm combining our notes and homeworks for week 9 and 10 together. So there'll be no actual homework due this week. I'll just have homework about indexes due next week. And again, the basic idea of indexes is that there are data structures used for making your SQL queries fast. And these are typically going to be the select queries that we're most interested in, that when you have, say, a table that contains terabytes of data in it, we want to be able to do those select statements in just fractions of a second rather than the hours that we were waiting for that MapReduce process. What we'll see is that the advantage of using the indexes, there's sort of two of them, but the main one is that you reduce the runtime of finding a row in the table. And so finding a row in the table is required for select and update and delete statements. We'll reduce that down from linear time to log n time. So that's a huge, huge reduction, that log n is basically free. We'll also see that they are required for these unique constraints and really, really useful for the foreign key constraints that we've been taking advantage of so far. The disadvantage, though, of indexes is that they increase the runtime of our insert operations. That insert operations would normally be constant time, but it'll go up to an O of log n time. So it's a small penalty. Again, log n is essentially free, but it's not completely free. And so if you make too many indexes, you'll get some performance penalties that way. And so finding the right balances of which indexes to create and exactly how to create them is sort of the key challenge for most big data problems involving runtime. And how do you make your things go faster? Yeah, so I'm saying here that this is going to be 90% of all big data runtime problems. And then we'll, after we're done talking about indexes, we'll start talking about those other 10% of problems in this class, say in about the last 3 weeks or so of class. These two comics that I have for the week are, the general idea is of both of these comics is that you have these two web programmers or back-end programmers. Somehow they've been struggling getting their code to run fast, and then this SQL wizard pops up, creates a perfect index, and makes things just drop in runtime down to nothing. And so that's what hopefully you will be after we finish this section of the course, is this SQL wizard who can make things just instantly fast. Any high-level questions before we get started with the details? Okay, so in Postgres, there are 7 types of indexes, and we'll go, at least at a high level, we'll go over all of them in this class. But the B tree is the most important index. It's sort of foundational for all the other ones, so that's what we're going to spend the most time on. And then this gin and this rum index are also really important for full text search and making things like our search engine that we're building up to practical. And so we'll spend a lot of time on those 2 indexes as well. So the B tree. We're gonna switch screens over here to this little area where I can draw, and we'll talk about the B tree. And we'll start by talking about, I guess, first what the B tree is not and what it's inspired from. So you might remember from your data structures class, hopefully remember your binary search trees. And the idea of the binary search tree is you have, we'll say we have some elements that are letters of the alphabet, and you organize your collection of letters by if a letter is less than or before in the alphabet, whatever node you have, whatever value is in a node, it goes to the left. So here we might have the letter D, and up here we might have the letter O. And if it's greater than the node, it goes to the right. And then, so over here, say something like A. And then maybe here, something like B. And then like this with a C. And so this is a valid binary search tree because it satisfies that binary search tree property of things that are less than go to the left and things that are greater than go to the right. And in the best case scenario for a binary search tree, when the tree is balanced, you get logarithmic lookup times. That in order to find an element, it takes log n time. The problem with the binary search tree is that we don't typically get this best case scenario. There's no guarantees that we're in this good scenario. That this tree right here, we would call this tree unbalanced because it does not get that good behavior. If I want to find the C, I have to go from G to D to A to B to C. And so after the binary search tree in your data structures class, you introduce some sort of balanced binary search tree. And the particular balanced BST that I like the most is called the Avl tree. But other instructors will go over different trees like the red-black tree is another popular one. And so you might have seen one of these two before or a different balanced binary search tree. And the idea of the balanced binary search tree is we add more rules to the tree, add more rules that the tree must satisfy somehow. And this guarantees the tree will be balanced. And it'll be some sort of approximate balance, but it'll be enough balance that we get the O of login lookup time. And typically it's going to be O of login, not just for lookup, but for insertion and deletion, updation, all your basic sort of tree operations. And just to be complete, we'll redraw this tree over here in a more balanced fashion, like make D the root, and then to the right of D, we'll have G, and then O, and then over here, A, B, and A, and C like this. And so this green tree over here is clearly a better tree structure than this blue tree because it has this balanced property. The disadvantage of the Avl tree, this is usually where we stop in the data structures course talking about trees. The disadvantage of the Avl tree, or really any balanced binary search tree, the fundamental disadvantage is that the data must be contained in memory somehow. Data must be contained in memory. And I'll put must in quotation marks because it doesn't necessarily have to be, but all the implementations that people actually do are going to be placed in memory. And this is a problem because in these big data situations, say we have terabytes of data, you probably have terabytes of hard disk space, but don't have terabytes of RAM to put your Avl tree inside of. And so what we need is a tree structure that's still balanced, so we still get the login lookup characteristics, and that's designed to be implemented both on a hard drive or in memory, kind of swapping back and forth as needed. And for the remainder of this time, instead of saying hard drive or writing out hard drive every time, I'll just abbreviate that as HDD. On a hard drive and RAM. And this is where the B tree comes in. B tree solves this problem. So maybe before talking about the B tree, are there any questions about anything that we've talked about so far and like what the need for the B tree is?
So why does the standard BST require data to be in the memory?
Yeah, it's a good question. So the question is, why does the standard BS tree require all the things to be inside of memory? And maybe we'll answer that a little bit when we talk about what the B tree does differently than the BST. But essentially, what we'll see is that the binary search tree is going to be very inefficient when it's implemented on a hard drive, because the thing that actually takes up most of the computation is going to be going from one node to the next. And that'll turn out to be inefficient with a binary search tree. Yeah, so it's a good question. The actual definition of the B tree will help illustrate that. So a B tree is a search tree that's not binary. The basic idea, the first main concept of the B tree is that it's not binary. So instead of having our node contain only one element inside of it, it'll contain like a vector or list inside of it. And we'll use this as an example. D and J and O. So it has three things inside of it, this particular node right here. And then each one of these elements inside of it is going to have both a less than and a greater than side, just like the normal binary search tree does. So less than on D will go over here, and inside of there we'll have an A and a B, and then the greater than on D will be the same as the less than on J, and inside of here we'll have F and H. Similarly, the greater than for J is going to be the same as the less than for O. And here we'll do K, L, M. So this one will have three things inside of it. And then there'll be a greater than side for the O, which will have a P and a Q. So the B tree is not binary. It can have things in the middle, children off the middle, and it contains more than one element per node. We call the number of elements per node this is sometimes called the branch out factor. Or the fan out of the tree. And one of the other properties what actually makes a B tree instead of just a non-binary search tree is that it satisfies the property that the number of elements per node is less than or equal to some number B and greater than or equal to that number B over 2. So there's a lot of sort of confusion about actually where this name of the B tree comes from, what this B stands for. The B tree was invented by people who work at Boeing. So some people say the B stands for Boeing. The B tree is typically presented with this rule right here, where the B is used as a bound on the number of elements per node. And so some people say the B corresponds to this B right here. The actual authors of like the original creators of the B tree, they said, we have no idea, we just like the name B tree. And so it doesn't really stand for anything in the same way that other data structures, the names have meaning. And because this B is not really the same as this B right here, you'll never see, for example, nobody will ever see you'll never see somebody say a 4 tree. That just doesn't make sense. People won't say that. Instead, they would say a B tree where the fan out is 4. Up here, this B tree is would have a B value equal to 4. In this B tree up here, B equals 4, because every node has satisfies this bound, that the number of elements in the node is less than or equal to 4, and it's always greater than or equal to 4/2, which is 2. So this is a valid B tree with B equals 4. There's one other property that a B tree is supposed to satisfy, and that's that all leaves must appear on the same level. So here we have 4 leaf nodes, these 4 nodes right here, and they all appear on the same level because they're all down here at the bottom. If we were to, say, add another child off of this queue going off to the right, down over here, then it would not be a B tree anymore. It would be some other type of balanced non-binary search tree. So let's see. Let's talk about the what the lookup sort of operation looks like on a B tree, and then we'll talk about why the B tree is more efficient for disk-based operations than the binary search tree, and that'll answer hopefully your question, Sapvik, about why the BS tree is not suitable for implementing on a disk. So first of all, what does a lookup operation look like? It's essentially the same as in a binary search tree, that if you're looking up, say, whether a certain letter, say we're looking up whether the letter C exists in our tree, then you start at the root node, you find which one of these intervals the letter C is between. C is less than D, so we go left over here, and then you check this node over here to see if C is contained in that node. It's not, so so you would return false. The runtime for lookup well, what we're going to have to do for the lookup is for each node in our, or for each value in our node, we'll have to check whether the thing that we're looking is less than, greater than, or equal to each value in the node. And then we'll have to do that exactly once for every level in the tree, starting at the root and then going down and possibly going down and down further. So the runtime of the lookup is going to be O of B, where the B comes from the fact that we have to do a comparison check on each of these elements times the height of the tree. And this height is always going to be O of log base B of n, where n is the number of elements in our whole container overall. The log base B comes from the fact that we are dividing things into chunks of size B. So the total number of levels that will have to go down is not log base 2 like it is in the binary search tree, but log base B. And so this whole thing is going to be O of B log B of n, like that. Are there any questions about where that runtime comes from?
So wouldn't we just write that as O of log n to the base B? Because that's just a constant, right? B.
So in this case, B is not a constant. We don't want to treat B as a constant. You're right that if we were to treat B as a constant, then this would just be O of log n. But we want to consider what happens as we adjust the value of B. So what will happen as we make, say, B bigger? If we were to double the size of B, how will that affect our runtimes and the different operations that we're doing? So yeah, in this case, we'll be considering both b and n as variables and not constants.
Okay, that makes sense.
So related to that question, it makes sense to ask, let's think about different values of b and how is that going to affect our runtimes? And there's a very simple result that I'm not going to prove, but hopefully you'll be able to demonstrate this for yourself, but that b log b of n is going to be strictly greater than the log base 2 of n for all b greater than or equal to 2. So this log base 2 of n is the runtime for doing searches inside of a binary search tree, a balanced binary search tree like an Avl tree or a red-black tree. And this right here is going to be the runtime of doing our searches in a B tree. And as we increase this B value, as we make it larger, we're actually going to be making our runtime take more time. We're going to have to do more comparison operations in order to go find our elements in the tree. So as B increases, we'll need to do more comparison operations. For a normal data structure, like in a BS tree or an AVL tree, we measure our runtime of the data structure in terms of the number of comparison operations that we have to do, counting the number of comparison operations. So runtime is typically proportional to the number of comparisons. And that's also true for a standard B tree as well. But it's not true when hard drives are involved. And so we're gonna take a detailed look at this point right here. We'll see exactly, talk for 5 minutes or so about like how physically a hard drive works. And then we'll come back, once we do that, we'll come back and re-talk about the runtime of a B tree in terms of the how long it takes when it's implemented on a hard drive, and compare that to the runtime of a BS tree, a binary search tree implemented on a hard drive. So we're going to go analyze this line right here in detail next. And in order to do that, I'm going to switch my screen back over to our README file, and we'll take a look at the internals of your typical HDD. So yeah, what we're going to talk about right now is specific for HDD, these hard drives that actually have a physical hard disk inside of them. What we're going to talk about is less true for the SDDs, your solid state drives, but it's still order of magnitude true, things that we'll be talking about. And because hard drives, HDDs, are actually still significantly cheaper than solid state drives, most large-scale data storage systems still rely on HDDs, hard drives, as their main storage technique. So this is a schematic of the inside of a hard drive. And the important parts here are that you have these platters, these disks. These are the portions of the hard drive that are actually physically moving, spinning around. And these are the portions of the hard drive that actually physically contain your data inside of them. Then you have this needle right here called the recording head. And this needle has a magnet inside of it. And when that magnet gets close to the spinning disks, it can either detect whether there's a 0 or 1 located in that location on a disk, or it can change that location to whatever value you want it to be. And this disk spins around really fast. A typical hard drive is spinning at 7,200 RPM, which is about 120 revolutions per second. So these are spinning really, really fast. And then this, anytime you want to find a new location on the hard drive, if it's on the same track, so we call the hard disk itself is divided into tracks, where each track is a circle that goes around the platter here. And the bits are located sort of in a circular fashion following that track around the platter. If the location, the next file that you're looking for is located on the same track, then you basically don't have to do anything in order to read it. You just wait a fraction of a second and the disk will spin a little bit and be under your recording head right here, and then you can read it again. But if the bits are located on a different track, then this recording head actually has to move, and that's a really slow process. So in order to move from the end over here, or from the middle to the end, it's maybe, say, 1/10 of a second, so it's kind of fast. But if you have to do that for every sort of bit of information that you're trying to access, that's a lot of movements of your recording head, and so it's going to take a long period of time. Fundamentally, when you're reading stuff, when you're reading information from a hard drive, the fundamental limitation is how fast can this recording head move. That if you're reading bits that are what we'd call sequential bits right after each other, the recording head doesn't have to move at all. It just sits there continuously streaming off the bits as the platter spin. But if the bits that you're reading are not sequential, then this recording head has to move around a lot in order to do that reading. And so what we're going to try to do is minimize how much movement that this recording head has to do while it's accessing our index, our data structure. One last sort of thing to talk about with these platters is exactly how the data is physically stored, it's saved onto these platters, and that's shown in this figure down here. So this is sort of a cutaway of these platters. There's typically maybe 12 or 16 platters in an individual hard drive unit, and those platters are arranged where the tracks that are closest to the middle of the platter have the smallest amount of data on them, the fewest of what we call sectors. Each track is broken up into sectors that contain typically about 512 bytes inside of them, some multiple of 2. It's different for every platform. And because there's more disk space, physical actual disk space on the physical disk, farther away from the center, you can have more of these sectors or more bytes located in this region of the hard drive than you can in this region. And so you'll also be able to actually read data faster from this far end of the hard drive than you can in this end of the hard drive right here, because it's farther away from the center, it's spinning faster, and so more bits per second will be flying underneath your recording head and able to read it. Are there any questions about the physical implementation, what's going on inside of a hard drive right here? Okay, then let's take a look at some numbers about exactly how long it takes to access information on these hard drives. And so this is the website right here, norvig.com. Peter Norvig is a famous AI programmer. He used to be a professor, but now works at Google. And he and his team at Google have developed this this table right here as what they consider to be runtimes that every programmer needs to know about how hardware works. And we're only going to look at a couple of these here. But the first one we'll look at is this executing a typical instruction. And you can see that it takes 1/1,000,000th of a second, or 1 nanosecond. And if you think about like the CPUs that you may have seen advertised, they're like 3 gigahertz or on that range of speed. And the gigahertz is billions of operations per second, billions of cycles per second. So it's 3 billion cycles per second. A typical operation on a modern CPU can take anywhere from, say, 1 to 10 cycles, depending on exactly how, what the operation is. Something like a comparison less than greater than, that's going to be on the order of 1 cycle, but more complicated instructions can take more cycles. So on average, just approximately 1 nanosecond. The next thing for us to look at is this fetch from new disk location, or a seek operation. A seek is what we call it when this recording head has to move from one location to another. And the exact time that that's going to take is going to vary from hard drive model to hard drive model, and from like exactly how far that you have to move this recording head, whether it's going all the way from the center to all the way to the outside, or just a little bit of movement. But on average, that takes around 8 million nanoseconds. So 8 million times longer than a typical execution instruction. 8 million times longer than doing a less than or a greater than. And so if it almost doesn't matter like how big your data structure is, how many comparisons that you have to do less than or greater than, if you have to do a single one of these seeks. The amount of seeks that you have to do, the amount of times that hard drive head moves, is totally going to dominate the runtime of accessing information on the disk. Another really good quantity to know is this one right here, read 1 megabyte sequentially from a disk. So this takes a little bit longer than doing a seek. It's 20 million nanoseconds. Remember, this is 1 megabyte and not just a single byte. And so if we were to average this 1 megabyte over all of the bytes that actually get read, mega stands for million, so it's 20 million divided by a million, so about 20 nanoseconds per byte. So actually reading the information from the hard drive, once you've found it, is really, really fast. But you can do that almost as fast as you can process the information. That if you had 20 instructions per byte of information, then you're a very efficient coder. And so these sequential reads from disk, they sort of don't matter as much, but this seeking from the disk, this matters a lot. And that's what we want to minimize. So that's the key thing about why we use the B tree, is because it ends up minimizing the number of seeks that we do on a disk. That on the B tree, each one of these nodes is going to be physically located right next to each other on the hard drive. And so as soon as we start reading from this D location, it's very quick to get access to this J and this O. But once we've decided that, okay, I need to go between the D and the J down to this node right here, I have to do a disk seek to get from this location down to this location. And that's the thing that's going to be really, really expensive, is that disk seek. Anytime you're traveling from one node to another node, that's the expensive operation when you're navigating trees on a hard drive. So we don't actually care about the number of comparisons that are happening. What we care about is on the hard drive, we care about the number of nodes that we access. Because each node access is a seek. So each node access requires physically moving that disk head to a new location in order to find it. So in the B tree, there a little bit. In the B tree, the number of nodes that we have to access in a lookup is O of log base B of n. So we remove that B factor out front, that B factor came from the fact that there were B elements inside of the node, and so we had to do a comparison with each of those. But when we take that out, and we're only counting the number of nodes, and we get the log base B of n. Whereas in the binary search tree, we get that it's log base 2 of n. And so by increasing this B factor right here, we can shrink the height of the tree and reduce the number of seeks that we end up needing to do. This is the sort of the key difference between binary search trees and B trees, and why we use B trees whenever you're using a hard disk somehow. So if there's one thing to remember, it's just this part right here. Are there any questions about this?
Mike, is it still effective to use B tree for solid states?
Sorry, can you say that again?
Is it still effective to use B tree on solid state drives?
Yeah, it's a good question. So for solid state drives, the physical implementation, whoops, here we go. The physical implementation is very different than this, but it still turns out that you have this effect where it's much faster to read things sequentially than it is to read things, so what we call random access all over the place. And the reasons for that are a lot more complicated than they are for hard drives. And the order of magnitude is much smaller. That a random access is about twice as slow as it is in a sequential access for a solid state drive. But we still typically use B trees on solid state drives, that they outperform binary search trees. There's a new type of solid state drive that is sort of just in the past year or two becoming popular, called Nvmes. These are actual, so they're the fastest permanent storage that we have right now. They're just as fast as RAM that you stick in your computer, and they actually attach to use the same hardware buses internally as RAM. And even in these most fast things, it's still more efficient to do sequential access than it is to do random access. So any sort of permanent storage, people always use B trees for over a binary search tree. That's a good question. Any other questions so far? Okay. In this class, we're not going to focus on the sort of insertion and deletion operations. I'm not going to ask you to reproduce those at any point on the B tree, but I'm going to just real quickly show you what those look like. The insertion operation, because the insertion operation is fairly simple. When you insert inside of a B tree, what you do is you do a search for the item, and then insert into that node where it's at. So let's say we wanted to insert the letter R into this tree. We search, find R right here, and insert it. And then we could insert S just fine like this right here. And we can insert R and S directly because it doesn't violate this B less than or equal to 4 constraint that we said that this tree has to satisfy. As soon as we try to insert the T variable though, like this, inserting T right here, then we would violate the constraint. And so what happens is we just break this up into two different children of this node up here. And I'll draw out up here what that looks like. So the root goes to D, J, O, and then I'll bring this R up top like this. The left of the D stays the same as before. This stays the same. This stays the same. These three boxes correspond to these three boxes right down here. This O box right here corresponds to PQ. Everything to the left of the R that we brought up, and then the ST comes over here. ST to the right of the R. If we were to keep adding things, say, a U, a V, and then a Y, then we would have to add another thing up here. We'd then break the constraint up here that it's less than or equal to 4, and so we'd split that once again. And that's how you add new levels to the tree, is when the root ends up splitting. So it's a relatively no sort of like deep magic involved. The insertion operation's about as simple as you can have for these for these balanced trees. The deletion operation's a little bit more complicated, so we won't go over that at all. The problem with, or there is a minor problem with this insertion operation, and that's going to lead us to the next data structure that we'll talk about, called the B+ tree. And the B+ tree is actually what's implemented in Postgres and most other databases. So I'll describe what the B+ tree is, and then we'll see that the B+ tree has a really, really simple creation algorithm. It's almost trivial, and that's why it's so widely used. So the B+ tree is a B tree. Sometimes people will write B tree with this dash and sometimes without. I'll end up doing it both ways throughout the notes. It's a B tree, but all data is only stored in the leaves. I'll draw a picture to illustrate exactly what this means. So with our B tree that we had before, we had an A, a B, and a D, and an F. And then we had an H, K, L, M, and we also had a OPQ, OPQ, like this. And so this is all the data that we had in the B tree that we had before. And now the values down here in the leaves are different than we had before, because I moved the things that used to be in the root node down into the leaves. And the root node, all non-leaf nodes, will just contain duplicates of the information inside the leaves. So here we'll have an F that goes here, and then an M that goes here, and an that's it. Just two elements here, F and M, pointing to these. So this F right here duplicates this, and this M right here duplicates this. Now when we're doing a search, everything to the left is less than or equal to, everything to the right is strictly greater than, left of the M less than or equal to, everything to the right of the M strictly greater than. The simple and creation algorithm for this B+ tree algorithm is to just first sort the data, then divide it into its B-sized partitions. And up top, and the last thing is add the internal nodes. Adding these, so the internal nodes referring to everything that's not a leaf node. This, this creation algorithm turns out to be anywhere between 2 to 10 times faster than adding things one at a time. Asymptotically, they both end up having the same runtimes. It's just the constant factor is much better for this B+ tree creation algorithm. And it also ends up reducing the number of nodes that you actually need. So to see what this reduces the number of nodes needed means, if you look at this tree right here, you can see that I've constructed it so that all of the nodes are sort of as full as possible. That starting from the left, it's full, and then it's not full, but that's just because we don't have enough data to stick inside of it. If we were to look up at our B tree example though, so keep scrolling up to here, see that we actually, it's the same data contained here, but it actually requires more nodes because these left-hand nodes are not totally full. And this can happen very naturally when you're inserting things in an unsorted order that if we say had this used to be A, B, D, F, H, and then we split it to get this structure right here. And now we're stuck with these nodes that are only sort of half full. So asymptotically, they'll have up to a constant factor the same number of nodes, up to a constant factor the same runtimes, but just in practice, the B+ tree is a lot faster. Another nice advantage of the B+ tree is that it's really good for range queries instead of just, say, a single element query. And let's say what I wanted to do was find all the elements that were less than or equal to D, let's say, where D is greater than or equal to, sorry, I wrote that wrong again. D is less than or equal to my search term, it's less than or equal to O. Then what I want to return is DFHKLMO. And if we just add little pointers like this, basically storing this node on the hard drive immediately following this one, and this node on the hard drive immediately following this one, then I can easily just start reading here and keep reading up to here, and I don't have to do any seeks at all. It's all just one continuous long read like this. If we were using the B tree, then in order to answer a query like this, I would have to jump from my leaf node up to an internal node, back down to a leaf node, and you couldn't have everything sequentially arranged like this. So the B+ tree also makes your queries faster as well because of this structure. Are there any questions about the difference between the B+ tree and the B tree? Okay. So these two data structures are just like abstract data structures that can be implemented in any context. They could be implemented inside Postgres, outside Postgres, Python, C, whatever language. They're just generic sort of data structures. What we'll talk about next is some of the Postgres specific details about these data structures. So Postgres, again, uses the B+ tree instead of the B tree, but everywhere in the documentation, it just calls it a B tree. And this is pretty standard in any database or big data context. When people are talking about a B tree, they almost always actually mean a B+ tree. It's only when people are really talking about the internal structure of the data structure itself that they bother to make a distinction. And actually, the Postgres' internal B+ tree includes a number of additional operations or additional improvements besides the standard B+ tree that we haven't talked about here. So it's actually called the YAO B+ tree after the author of all of those specific improvements. But some of the things that are important for our purposes are that each one of these nodes, each node is represented or stored physically on the hard drive as a page. And we were talking about pages in the context of tables earlier. And so recall that a page is 8 kilobytes large. And it has some small amount of header information at the top, 40 bytes. And then the tuples are just stored inside of that page. And the branch out factor of this, so the number of elements that fit in a particular node, is not hard coded at some particular B number. And instead, it's just however many will fit into the page. So for Postgres, everything in orange is Postgres specific. B is different for each node potentially, and it's just the number of elements that fit in the page. Typically, if you're, say, indexing a very small data type, so like an integer that's 4 bytes, then, well, you can fit a lot of 4 bytes into this 8 kilobyte size. And so you'll have a fan out factor that's very large, potentially up into the thousands. If you're indexing something like strings, strings can be relatively large. And so you could have a fan out factor actually as low as 4 with strings. That in Postgres, there's a hard limit on the size of strings that can be indexed. And that limit is 2,000 characters, so that it can fit 4 different strings inside one of these blocks. In the regular tables, the pages for a regular table, the tuples can be toasted, but inside of an index, the tuples cannot be toasted. So there's a hard limit on the size of one of these entries inside the table. The next Postgres specific concept is exactly how the index relates to the underlying table. So recall that the table is just a collection of pages. So there's one page, there's another page, and so on. Each one of these pages has some tuples inside of it. This. And each one of these tuples has a tuple ID, or a TID. So we'd also seen before the object IDs and the transaction IDs. So there's a third type of ID. Here, this T does not stand for transaction. In Postgres, transactions are X's, and this T stands for tuple. And its format is always a 2-number pair, so something like 3, 2. where this first number refers to the page number, and this second number refers to the tuple location inside of the page. So the tuple number in the page. So if this is, say, tuple 0 and tuple 1, this is page 0, page 1, then the TID of this particular location, TID equals 0, 1, like that. Inside of, so the index is also going to have a relation. The relation is just a set of tables or a set of pages. This one over here is the index. This one over here is the table itself. And inside of the index, we're going to store our tuples. Or what a tuple is storing is what the column is that we're indexing, and the some auxiliary information. There's two types of pages. It can either be an internal or a leaf page. The tuples in the internal pages, they store the data and then the reference to the other location in the index. To the index, whoops. And then in the leaf page, an individual tuple will still store the data, but then it'll store a tuple ID, TID. The way this is commonly, or one other way this is commonly drawn out in pictures using that actual sort of more traditional tree notation. If we had our, so the same B plus tree that we had before of, we had F and L up top. Sorry, that's an F and an L. Then down here, A, B, D, F. This A right here would need to point to the corresponding location inside of the table, point to the tuple ID inside the table. So for a leaf node, this arrow right here is this reference to the index. It's actually a TID inside of this index table like this. And this TID in the leaf node is the reference into the table itself. The key thing to take away from this, make sure that you understand, is that the index over here contains, each tuple contains both a data element and a TID. This data element is not the same as this tuple over here. Not the same as the table tuple. And so in order to actually, if we've used our index in order to actually look something up, in order to actually get, say, the full row out of the table over here, we need to first find in the index where our condition is stored, where the data is stored, and then in our TID, we get that TID and look it up in the table over here. There's a potentially very confusing representation about how the indexes and the tables relate to each other. So are there any questions about that?
So this data that is stored in the index, what data is that? Is that like something that tells us what is stored inside the table?
That's a great question. Yeah, so the question is, what exactly is this data that's stored inside the index? And this is something that we haven't explicitly talked about yet, but it's important. So let's scroll down here to see an example. Let's say we had a table that was like a create, has the following schema, create table A as, and then we'll have an ID that's a big serial and a name that's text and a created at that's a timestamp, and potentially a whole bunch of other fields like this. Then the tuple that is stored in the table object is all of this information right here. What we'll do is, and we'll see the examples of running the actual SQL code in the next class, but in order to create an index, you use a command that looks like create index, then it's the name of the index, and then the name of the table. So in this case, my table's name is A, and then in parentheses right here, would say what column you're creating the index on. So we'll say I create the index on the ID. Then this ID right here, the thing that goes right here, that's the data portion of the index. Whatever column you put right here, that is the information that gets stored inside of this index table. And that is the information that's used in the comparisons for doing the not binary search, but the tree search through your B tree. And then once you have found a leaf node that contains, say, the ID right here, then it would point to the table over here. Did that help answer the question, Satvik, or do you have more questions about that?
Yeah. So okay, so that makes sense. But then why would there be a question of using strings and stuff? Because we can just use like an int, and that would be much more, we can store a much larger b value.
Yep, this is a great question. So here, we've created an index on this integer, this big serial. And what this will support for us is now if we were to do a select query like select star from A, where, for example, ID equals 100. Now we can efficiently do this select statement because we have an index on ID here. We have a B tree that's created on ID. And so we can traverse that tree to find where ID equals 100. And then once we have that, we look up in the table itself to get the star, to get all the other columns besides ID. But what if we had instead select star from A, where name equals Mike. Now this variable right here is, we say there's no index created on this variable. And so there's, even though we have an index on ID, we can't compare this name to the values inside of the ID. And so the only way for us to do this particular select statement right here is to actually just scan through the entire table and taking the linear time to do that. In order to make this query faster as well as this query, I would have to create an index on this string right here, doing create index. So some other name on a name like this. And now that the data in the index, the thing that we're doing less than and greater than on, is the name column. And so we can search efficiently now through this name column to extract the appropriate TID and then get the rest of the table contents. So the particular indexes that you create is going to, what we'll see is it depends very, very heavily on which queries you want to be running on your database. That for every query, there'll be some particular index that will be a good index to create for that query, and you'll want to make sure that you only create those indexes that are appropriate for the queries that you actually need. Next time in class, we will go over sort of in more detail the relation to the actual SQL, what we kind of started talking about now, to these relations up here. And we'll actually see the internal algorithms that Postgres uses to map, to actually map from a query onto the data. So if that still seems fuzzy, that's okay. That's what we'll clarify next time. Any other questions today? Okay, so the big takeaways from the things that we talked about today, that the B tree, it's not binary, and the key thing that that lets us do is the number of nodes in a lookup is going to be O of log base B of in. And the number of nodes is what's going to dominate our runtime, because that determines how many seeks we have to do on the hard drive. The inside of Postgres and really every database, instead of implementing this raw B tree, they implement this B plus tree, which stores the data points sequentially in the leaf nodes, which further lets you reduce the number of seeks that you have to do in certain situations. The last thing is that the fan out of these nodes in Postgres is determined by the combination of the page size and the size of your actual elements, and is typically going to be fairly large, on the order of like 100. And because the fan out is very large, when you do log base 100 of a really large number, you're going to get a very short tree. It's very common for a table that contains millions or even billions of rows to have indexes whose trees are only like height 3 or 4, very common. And so because of that, you only have to do 3 or 4 page seeks, these expensive disk operations, in order to access your data in the database. If you want a reference for the details of these operations, there's good references right down here, but this middle one is sort of the best reference. And it talks about the stuff that we'll be going over next class too. So with that, we'll end class for today, and I'll be available for anyone who has questions either about this or about the Twitter Postgres homework assignment.